Hello everyone, it's July 19th, a lovely Saturday. And you're listening to your one and only Senno Annie. Today, I'm super excited to dig into a really cool trending article from the archives that's all about the future of R&R. Let's get right into it. The title is Predictability-Aware Motion Prediction for Edge Trivia. High-Order Error-State Kalman Filtering. Phew, that's a mouthful, right? You can find it on ArcSynth, and the ID is 2507.13179. It's a bit long. So, let's break down what this paper is all about. Imagine you're wearing a super cool, lightweight fur headset. You're playing an awesome game, and everything feels so real. The reason it can be so light and comfy is because all the heavy-duty computer work, like rendering the graphics, is happening on a powerful computer nearby called an edge server. This is called remote or offloading. But there's a catch. When you move your head, there's a tiny delay before the picture and your headset updates. This is called Motion-to-Photon latency or net latency. Even a super small delay can make you feel dizzy or sick, which is a total bummer, and we call it Cybersickness. It completely ruins the immersive feeling. To fix this, computers try to predict where your head will be a split second in the future. But the core ways of doing this aren't perfect. One way is using deep learning. It's really smart and can make good predictions, but it needs a ton of computing power, like expensive kits. That's not great for edge servers that need to handle lots of players at once. The other way is using something called a Kalman filter. These are much lighter and faster, but they're kinda simple. They assume your head moves in a straight, predictable line, that in a fast-paced game, you're whipping your head around. And these filters just can't keep up. They also get confused if the network connection is spotty, and data packets get lost. So this paper introduces a brand new, super smart predictor to solve all these problems. They call their framework PsudoESKF, which is a special type of error-state Kalman filter. I think it's so cool. Here's what makes it special. First, it's predictability-aware. That means it has a motion modifier that actually analyzes how you're moving your head. It can tell if you're looking around slowly and predictably, or if you're making sudden, jerky movements, like you would in an action game. It does this by measuring something called entropy, which is like a measure of randomness in your movement. Second, it models high-order motion. So, instead of just predicting your head's velocity, it also predicts its acceleration and even its jerk. Jerk is like the change in acceleration. By looking at these higher-level details, it can make much more accurate predictions about your complex, nonlinear movements. You know what's really awesome? Does all of this without needing a powerful boom. It's so lightweight and efficient that it can run on a regular RAPU and an edge server. This makes it super practical and scalable for real-world use. Plus, it's way more robust against packet loss, so a shaky connection won't mess up your game as much. When you compare it to other technologies, the difference is like night and day. The standard Kalman filter or Kalker consistently lags behind the user's actual head movement. It's like it's always one step behind. But PsudoESKF, on the other hand, lines up almost perfectly with the real movement, with way less delay and overshoot, and compared to deep learning methods. This PsudoESKF gives you amazing accuracy without the massive computational cost. It's like getting the best of both worlds, high performance and high efficiency. So where could we see this amazing technology being used? Let me give you a few examples. First, and this is the big one, interactive R&R games. Imagine a fast-paced shooter or a racing game Ember. With this tech, the world would react instantly to your head movements when you quickly peek around a corner. The view would be there right away with no lag. This means you get a much more immersive experience, and you're way less likely to feel that yucky cybersickness. Second, think about remote collaboration and train Ember. Like, you could be in a virtual meeting room with coworkers from all over the world, where a medical student could be practicing a complex surgery in a High-Order simulation. For these interactions to feel real, everyone's movements need to be perfectly synced. This prediction technology ensures that when you turn to look at someone, their avatar is exactly where it should be, making the whole experience feel more natural and present. And for a third example, something a little different. Teleportation like flying a first-person view or filmed drone. When you fly a drone with a VR headset, any lag between your head movement and the drone's camera can be super disorienting and even dangerous. This predictor can compensate for that network delay, making the drone's camera feel perfectly connected to your view. This would be huge for things like search and rescue missions, or inspecting hard-to-reach places. So to wrap it all up, this research is a huge step forward for Motion by creating a predictor that is accurate, efficient, and robust. The authors are paving the way for a future where we can all enjoy incredibly immersive experiences on lightweight, comfortable headsets. That's a really practical and clever solution. That's all the time we have for today. Thanks so much for tuning in. This has been Sam Malcani, and I'll catch you next time. Bye-bye.